We just examined in the previous video how to find points and space on a Cartesian coordinate system. And now we're going to move into a conversation about slope. And you may be wondering, why do you have pictures of those colored blocks? Well, this is how you start the conversation of slope with children. And this is all about proportional relationships between two different units that have a constant rate of change. That's what slope is all about. Children might study the number of tiles that you see in each figure here and start with a very basic observation. If we number each tile, so this is each drawing, this is drawing 1, this is drawing 2, this is 3, this is 4, and we could keep going. You then just, so this is, we'll label this as the figure number. Often when we do that, we indicate it with the letter N for it's the number of the drawing, 1, 2, 3, 4. And here will be the number of tiles. The number of tiles. And we'll call this just capital T, just as an abbreviation for it. So figure 1 has 1 tile, figure 2 has 3 tiles, figure 3 has 5 tiles, figure 4 has 7 tiles, and et cetera, et cetera. And so you could have a lot of discussion with kids about what they observe, what they notice. And they might notice the blue tiles are the starting point, and then they add pairs of red tiles and then pairs of yellow tiles. And every figure after that, you're always adding 2 more tiles, plus 2, plus 2, plus 2, right? That's happening every time. And so they might be able to make a little table that organizes their information that looks something like this. In a table, we often even segment it with lines and grids, right? And so what that evolves to is being able to put that information into some sort of graphic representation. One of the things you'll notice is that I noted that from one figure to the next, each time we were increasing by a constant rate. As we went up from one figure to the next by 1, our number of tiles increased by 2. And one figure to the next here, tiles increased by 2. 1 here, 2 here. So again, that is called a constant rate of change. And in math, one of the symbols that we use for change is this triangle. It's a Greek letter, delta, and that is a symbol that's frequently used. And so when we examine this picture that you just saw right there, we describe this ratio of change as, I'm going to type it here. We talk about the change in the total number of tiles compared to the change in the figure number. In the previous video, I introduced the idea of independent and dependent variables. And in this particular situation, the figure number is our independent variable, independent, because it's just the number of the figure. The number of tiles is our dependent, because the number of tiles depends on which figure we are talking about. And so when we state our change, our ratio, we always are going to compare the independent variable, independent, to the dependent variable. And we're going to talk about the change in the independent variable compared to the change of the dependent variable. In this situation, that is comparing the change in tiles to the change in figure number. which is a ratio of 2 to 1. So this introduces the idea of what we're going to call slope, okay? What we're going to do next is take the information that we started to see in this tile scenario and actually put these as points on a graph so we can examine them. And so here is where I'm going to introduce to you the Desmos calculator. And let me just reset this. So I mentioned this in the previous video that this is a nice tool, and it's a graph, as you can see, and you can plot points on this graph. You can plot lines. I'll show you that later. But for right now, what I'm going to do is I'm going to go back to our diagram here and our table, and I'm going to plot each of these pieces of information as a coordinate pair. So the first one right here, this is going to be the point 1, 1. Remember, our figure number is our independent variable, so that comes first. Our number of tiles is our dependent variable, that comes second. For this point, it would be 2, 3. 2 is our independent, 3 is our dependent, and so on. 3, 5, 4, 7. And you might even follow along and do this on your own piece of graph paper. I'm just going to put those points onto our grid, and you can type them in with parentheses, 1, 1. And notice how when we do that, it automatically just puts the point right there. Click down to the next section. The next one was 2, 3. Notice how it puts it right there. The next one was 3, 5. It plotted that point right there. And the last one we had was 4, 7. And so what we have here is this row of points that actually show up in a line. Now, just so I can draw on this, I'm going to take a nice little screenshot of this, and I'm going to go back to our whiteboard and paste it right here. Shrink it so we can see it. And so let's examine this. Let's play with this a little bit. And so one of the things that you might notice is that these points are all in a nice straight line, right? We could connect them. Now, I struggle to do this with this pen system that I have going on here, but we do notice that all of these points lie in a nice straight line. We'll talk about that more later. But we have these 4 points based on, again, the number of tiles and the number of the figure. Often when we are putting things on a graph, we label our axes with the information. And so this horizontal x-axis, this would be the number of tiles. And our vertical axis, the y-axis, I'm sorry, that was the number of the figure. I misspoke. Let's do that again. So the number of the figure and the vertical axis was the number of tiles. And one of the things you might notice is that if we examine that idea of rate of change, as we increase in the number of tiles by 1, that's a move to the right on our x-axis. We increase, let's try to make it straight, we increase in the number of tiles by 2. And then we have this new point, 2, 3. As we do it again, we increase the number of tiles by 1. I'm sorry, I said it again. The figure number by 1, we increase the number of tiles by 2. And that is the same no matter how far we go on this graph. As the number in our figure increases by 1, the number of tiles increases by 2. And that's what we were talking about when we made that fraction, the change in tiles compared to the change in figure number was 2 to 1. And this is the idea of slope, because slope talks about the rate of change. So another scenario that's a real world situation involving slope is highways. So the roads that we drive on. Highway engineers measure the slope of a road by comparing the vertical rise to each 100 feet of horizontal distance. So as you're driving down the road, when you drive 100 feet down the road on a highway, the FHA recommends that you only can increase the road by 12 feet. Now, that's on a highway. So they want their highways generally flat for safety concerns. However, when you are on secondary streets, on back roads, that's not quite as important. And so there's actually a road in San Francisco that's incredibly steep. So it actually increases by 1 foot for every 3 feet that you're driving on the road horizontally. And so this is this idea of slope. So on a highway, for every 100 feet you drive this way, you can only go up 12 feet this way. It's an angle of 6.8 degrees, okay? So for every 100 feet horizontally, you can only go up by a maximum of 12 feet. However, again, that Filbert Street in San Francisco, if you go 3 feet horizontally, it actually increases by 1 foot vertically. That's an incredibly steep road. And so again, this is the idea of slope. It's always comparing your vertical change to your horizontal change. This one would have a slope of 12 to 100. This would have a slope of 1 to 3. Very, very different fractions. Now, we've started this conversation maybe in a little different spot than you expected, because in math, right, slope is really all about proportional relationships, and I keep saying that, a constant rate of change. And so again, this is an 8th grade standard here. Graph proportional relationships, interpreting the unit rate as the slope of the graph, comparing two different proportional relationships represented in different ways. Okay, so this is again where your students will be going, needing to understand those relationships. So that's where we've started this conversation, again, with pictures of tiles and conversations about highways. Where we're going to go now is connecting it to our Cartesian coordinate system and our lines. And so when we are looking at a graph, and let me pull up a picture of a line. So here's a picture of a line on a very simple graph. And again, we're going to get to lines in a little bit later. What I want you to first do is just examine this line and find specific points where this line is crossing two intersecting grid lines. And what I mean, I'll give you an example. So right here, if we follow this line, you'll notice that at this point right there, that line is crossing this grid line and this grid line. And if we follow it down a little bit further, we have to go down to here before that happens again. If we follow it down further, it happens again here and here and here. And we've now just identified several points that exist on that line on this coordinate plane. And I'm going to identify these 2 points as the ones I want to work with, point A and point B. Take a moment, please, and identify the coordinates of both of those points. So this first point is the point 0, 4, and the second point is the point 1, 2. And so I'm going to write those off to the side. A is 0, 4, and B is 1, 2. Now, when we are trying to find the slope, again, slope, rate of change, when you're given 2 points, there is a formula that we can use. But first, what we have to understand is that we are noting 2 different points, and both of those points have an x and a y value. Both of them have an x and a y. And so to keep them separate from each other, we often give them this little subscript notation with a 1 and a 2. We read this x sub 1, y sub 1, and x sub 2, y sub 2. Those numbers don't mean to do anything. They just are indicating which is one point and which is the second point. And again, it doesn't matter which one we're talking about. As long as you call both the x and the y 1s within the same point, and both the x and the y's 2s within the same point. And so if we want to find the change in the horizontal distance, or the change in the x values, we would do that by taking x sub 2 minus x sub 1. And then if we want to find the change in the horizontal distance, change in y, we would take y sub 2 minus y sub 1. And if we want to find the change in the horizontal distance, change in x, we would take x sub 2 minus x sub 1. And if you recall from earlier, we write these as a ratio or as a fraction. And so in this scenario, we would say our change in our y value compared to our change in our x value. Remember, dependent variable compared to the independent variable. That would be 2 minus 4, y sub 2 minus y sub 1, 2 minus 4, over x sub 2 minus x sub 1, x sub 2 minus x sub 1, 1 minus 0, 1 minus 0. If we simplify that, we have negative 2 on top and 1 on the bottom. And we say then that this is our slope. Sometimes we do even simplify this to a whole number, but it can be helpful at the very beginning if we do state it as a fraction, so we can see the vertical change and the horizontal change represented as numbers. Now let's connect that to the graph itself. Now in the example I did earlier, scroll back up here, remember we identified how we moved along this graph, 1 to the right and 2 up. We're going to examine this one the same exact way. If I'm going from point A to point B, I'm moving on my graph from left to right. We always read graphs from left to right. So I would go 1 to the right, which is a move in the positive direction, 1 space. But then I'd move 2 down, which is a move of 2 downward, which is negative 1. We can do it again, 1 to the right, 2 down, 1 to the right, 2 down. Notice how our vertical change is negative 2 each time, and our horizontal change is positive 1 each time. The way we again say this is, as we go 1 spot to the right, we go 2 down. We move 2 down for every 1 spot we move to the right. A couple different ways to read that. So this leads us to our definition of slope, or how we would calculate it. So here is our what we would call our slope formula. Now you might have heard of this as rise over run in the past, rise over run. What do we mean by rise over run? Rise is the up and down change. So the rise in this case was -2. It's the up and down vertical change. And the run is the change in x, the horizontal change. Rise over 1 can be stated as change in y over change in x, or y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And so let's practice this a little bit. If I just give you a couple coordinates. So we're going to find the slope. And the two numbers, the two coordinates we have are 5, 3 and 9, 11. So I'm not even going to give you a graph, just the 2 points. So we're going to find the slope. So I always suggest labeling this as x sub 1, y sub 1, x sub 2, y sub 2, just so we've identified which variable is represented by which number. And so we'll say that our slope is equal to y sub 2 minus y sub 1, 11 minus 3. 11 here minus 3 here, over x sub 2 minus x sub 1, 9 minus 5, 9 minus 5. Do those calculations, we see that it's 8 over 4, and if we simplify it or reduce it all the way, we end up with 2. So that is a slope of 2. If you wanted to know what that looked like on a graph, it would mean, again, that for every 1 spot you move this way, you would move 2 spots this way. 1, 2. That's what that slope is representing. And that's how we calculate it. Here is the, or let's actually do let's do one more of those. So let's try another one where you're finding the slope between these 2 points, 2, 9 and 5, 3. So take a moment to find the slope between those 2 points. So again, we use our formula. I always like to label my points first, x2, y sub 2. So our slope, one other important thing to note about slope, in algebra, it's often indicated by the letter m. M is always often representing our slope. And so the slope is found by taking y sub 2 minus y sub 1. In this case, that's 3 minus 9. And x sub 2 minus x sub 1 is 5 minus 2. When we simplify this, we get -6 in our numerator and 3 in our denominator, which this is a slope of -2. Now, in those last two that we saw, these are what those graphs would look like. Run of 4 and a rise of 8. That was the first example that we did here. And the one that we just did was a rise of -6 and a run of 3. And so you might notice that this first one had a slope of 2. It was a positive number. Notice how our line is going up. In the second one, we had a slope of -2. Notice how our line is going down. That's a really important thing to note when we're working with slope. So let's look at another sort of real world example, and it involves lightning. You've probably heard, it's the wrong thing. You've probably heard about how you can calculate how far away lightning is based on how many seconds it's been since you heard the lightning. Well, let's examine that momentarily. And so here's the first part of the problem, the first bit of information that we have. And it says an observer can estimate the distance to an approaching thunderstorm by counting the seconds between a flash of lightning and the resulting sound of thunder. Every 5 seconds, sound travels approximately 1 mile. So if you count up to 10 seconds before hearing the thunder, that means the storm is approximately 2 miles away. So here is your question then. I'm just going to move this up. So a couple questions. The first one, is the time and is the distance independent or dependent? Which one's the independent variable and which is the dependent variable? Then make an input and output table like we did to start this section with the blocks, corresponding to the times of 5, 10, 15, 20, and 25 seconds. And then finally, sketch a graph of what those coordinate pairs would look like and connect them with the line, and then determine what the slope of that line is. So take a few moments and see if you can dissect this information and finish that problem. So hopefully you had some time to analyze this. We have two pieces of information again. We have the time and we have the distance. Those are the two pieces of information. So my question then is, which is the dependent, which is the independent? Which one depends on the other? And so what we hopefully will hopefully notice is that our time in this case is going to be the independent variable. And the distance will be the dependent variable. Why is that? Well, in the scenario that we are looking at, like this one right here, if you count up to 10 seconds before hearing the thunder, the storm is approximately 2 miles away. So you're counting how many seconds, and then that tells you how far away is the storm. So the storm's distance from you depends on how many seconds it takes for the thunder to get to you. So the distance is then depending on how long it is, if you're trying to figure out that scenario. So that means the time is our X and the distance is our Y. So a quick sketch of a coordinate plane. This is our X, this is our Y, this is our time, and this is our distance. Okay. Then it said, make an input-output table. So I'm going to put my time first, and I'm going to put my distance second. And again, inputs and outputs. Time is the input, distance is the output. And we said to make time inputs of 5, 10, 15, 20, and 25 seconds. I'm going to make my table nice and neat as I can. A little grid system like this. And so for every 5 seconds that passes, our distance increases by 1 mile. So 5 seconds means we are 1 mile away. 10 seconds means it's 2 miles away. 15 is 3, 20 is 4, and 25 is 5. So there's our input-output table corresponding time to distance. Then we're going to graph these. So I already did this using that Desmos calculator. And you can see, here's what that looks like. 5 seconds on the time horizontal axis means 1 mile on our vertical axis. And you'll see points here, 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 and there. And then it said, connect them with a line. So I drew my line that looks like that. So to finish this up, I'll take a quick screenshot of that, and then we will go back so I can draw on it on our whiteboard. I'm going to take a picture of that and paste it right here. So then the question asked, what's the slope of the line? So if we consider it from the standpoint of how do we get from point A, I'll call this point A, and this point B. How do we get from point A to point B? And we can only move along those horizontal and vertical lines. We have to go 5 spaces to the right to go 1 space up. So if you remember our slope is always equal to our change in Y over change in X, or our rise over our run. In this case, our rise is 1 and our run is 5. So we say that this has a slope of 1 to 5. If you also consider the fact that this scenario had units of measurement, it was 1 mile per every 5 seconds, right? So sometimes our slope, when it has real world applications, will also have some units of measurement. But for now, it's fine for you to just say it's a slope of 1 to 5. And it's also important for you to know that when our line is a nice straight line, our slope is constant, meaning that to get from one point on the line to any other point on the line, it's the same change horizontally and vertically. It's going to be constant forever and ever, no matter how long our line is. Now we're going to end this video with a special analysis of slope. So I'm going to give you 2 points, and I want you to do 2 things. We're going to find the rise and run and the slope. So we're going to find the slope. And then also, I want you to graph them. So take both pairs of points, find the slope, and then graph. So the first one, when we use our slope formula, if you remember, it's y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So I'll label them x1, y1, x2, y2, and that will be equal to 5 minus 5 over 9 minus 3. When you simplify, it's 0 over 6, and any fraction where 0 is in the numerator is equal to 0. So we say that this line, the line between these 2 points, has a slope of 0. We'll go back to the graph in a minute. For this one, our slope is equal to x1, y1, x2, y2, 9 minus 3 over 4 minus 4, which is equal to 6 over 0. And hopefully you remember that when you have a 0 in the denominator, that's not allowed. You can never divide by 0. And so we say that our slope is undefined. When you have a 0 in the denominator, this fraction is undefined, or we can also say there is no slope because it's not allowed. So the line between these 2 points would have no slope when your slope is undefined. So what do the graphs of those 2 lines look like? Well, they look like this. So the first one, what do you notice that's special or unique about those first 2 points? They lie on the same horizontal line. Notice how they have the same y coordinates. They both have a y of 5 and 5. What happens when you apply the slope formula and you have the same y coordinates? You end up subtracting the same number, getting a 0 on top, and so you'll always get a slope of 0. So when that happens, you have a horizontal line. The slope of any horizontal line is 0. Remember, m is our letter for slope. M is equal to 0 for any horizontal line. Now, the exact opposite thing happens when we are looking at the second one. Notice how they have the same x coordinates, 4 and 4. This line crosses our x-axis at 4. If the x coordinates are the same, you end up subtracting the same number from itself in the denominator, which gives you that 0. And so when you have a vertical line, you'll always have a undefined slope, which means, again, we say there is no slope. So again, horizontal lines have a slope of 0, vertical lines have no slope. And then the other thing that's important to note for the earlier examples that we did, and I mentioned this one time, whenever you have a line that is increasing from left to right, because you always read your graphs from left to right, these are always going to be a positive slope. And anytime you have a line that's decreasing from left to right, this is always going to be a negative slope.